Yeah, the commutator x square comma px square is equal to. Four options are given. This question is appeared in 2024 June. This is actually a simple question. How to answer it? See, the commutator asked here is x square and px square. Actually, operators should be given, but it is not given. I have told you for some operators, the operator symbol they are not putting nowadays, right? Okay. Now listen, how to solve this problem? See, it's very simple. You keep this x square as such and separate this px square into two operators like this, px into px. You can separate this also. Okay, in any way you can proceed. Okay, but I am separating the px square operator. Now see, this is similar to, see, x square, you can take it as an operator a, and px, let me take this as one operator as b, the other operator as c, b into c. If you have a commutator of a comma b into c, this can be written as, you can write this as a commutator of ab into c plus commutator of, bring this b in front, b commutator of a and c. This is a well-known formula, commutator rule, okay, which is available in quantum chemistry. So I'm going to use this rule here. Okay, if I use this here, see how it goes right here. So this is equal to, so this is now a and this is b and this is c. Now in this case b and c are same operators. So we can separate this as x square comma px into px. I'll put operator symbol. Even if you don't put, nothing wrong in it. Plus, in the place of b, what is b? B is px operator into a comma b. Now what to do? I have given a formula. See, x square or x power n comma px. X power n comma px. This can be written as I into, sorry, I into h cross into n x power n minus 1. Okay, we can write like this. I have given a general formula like this, right? The n can be 1, n can be 2, n can be 3, right? So the n can be any integer, right? Positive integers. So if I put this here, see, in a similar manner, see here I have x power 2. So we can write this as, I h cross. Now in the place of n we have 2. So 2 into x power 2 minus 1 is 1. So you need not put that. Okay. So this is the value, and into we have the px operator. Okay. Plus, similarly here we have px operator in front. I'll put that. Then apply the same rule here. So we get I h cross into 2x. Okay, I h cross can be taken as common. So I h cross, and we have even the 2 can be taken in front. 2 into I h cross. So here we have px into px, and plus here we have px into x. Okay. See, x into px, px into x, they may not be same. Okay. So this cannot be simplified further. Therefore, the correct option is, the correct answer is 2I h cross into x px plus px into x. Okay. So the correct option for this question is option D. Very simple question. You can easily answer this. Okay. Then let's see next question. The raising and lowering operators are denoted as L plus and L minus respectively. The correct commutator relation between angular momentum and its various components is. Okay, just go through the question. Once again, let me come.
Yes, sir.
Right. See, what is meant by the raising and lowering operators? They are called actually ladder operators. Okay, what's the meaning? Listen, what is meant by L plus and what is meant by L minus? And how it is connected to the angular momentum operator. So that's the question we have to discuss. L plus operator is called raising operator, which is nothing but Lx, x component of angular momentum, plus I into y component of angular momentum. This is nothing but L plus. Similarly, what is L minus? It is called lowering operator. Okay, so L minus is equal to Lx minus I into Ly. This is actually called the lowering operator. Okay, now what we have to do? We also know that L square operator, L square and Lx, the commutator value of this is 0. L square commute with the Lx. Similarly, L square commute with the Ly. And L square also commute with the Lz. This we know already. And I have told you, if two operators commute, they must have simultaneous eigenfunctions, or they have common set of eigenfunctions. Okay. Now, see in all the options, see the options carefully. They are asking commutator of L square L plus, okay, which is equal to commutator of L square L minus, equal to some values are given. Okay, here H cross into Lz, here H cross into Lx, here H cross into Ly, and here 0. So we need to find what is the commutator of L square L plus. Remember, commutator of L square L plus, commutator of L square L minus are equal. So this is the first point you should keep in mind. Commutator of, see, this is a very essential point. Keep this in mind. Commutator of L square, okay, it commute either with L plus or L minus. I'm sorry, they are actually equal. So L square commute with L plus, L square commute with L minus. The commutator values are equal. Okay, they whether they commute or not, we'll discuss. But this commutator value and this commutator value are equal. Keep that in mind. Now what I'm going to do, you find any one, because since they are equal, you find any one and see whether it is equal to H cross Lz or H cross Lx or H cross Ly, or it is simply 0. Okay, yes, how to do that? See what I'm going to do. I'll take L square. I'll take L square. L square, how it commute with the Lx, we'll see. L plus, L plus is equal to L square, comma, L plus is nothing but Lx plus I into Ly. This we know. So this is A operator and this is B plus C. I have B plus C now. So you can separate this by using commutator rule. L square Lx plus I into L square, comma, Ly. Okay. Now I have already told you L square Lx, they commute with each other. So the value of this is 0 plus iota. L square Ly also commute. So this is also 0. So 0 plus I into 0. So the answer is 0. Okay. So these two, that is square of the net angular momentum operator, right? It commute with L plus it also commute with L minus. Okay, so for this question, the correct option is option D. Right? Take down. Yeah. In Huckel approximation, the pi electronic energy for the cyclopropenyl cation is. Okay, pi electronic energy we need to find out, and the given system is cyclopropenyl cation. Right? Yeah, it's a simple system. You know very well the cyclopropenyl cation. Let me draw like this. Cyclopropenyl cation. Okay, it's a cyclic system, and I have told you as per the Frost cycle, right? You draw a triangle, equilateral triangle, and you should draw in such a manner that the one end of the or one corner should be always at the bottom. Okay, so draw the triangle in such a manner, right? And the other two corners, they are in the same position, which means these two levels or these two energy orbitals are degenerate. Okay, and this is the center of the circle, also called barycenter. Now the energies below barycenter should be given positive symbol, and the energy above the barycenter should be given negative symbol, right? And in cyclic system, the energy of the lowest level is always alpha plus 2 beta. For any cyclic system, cyclic conjugated system, the energy of the lowest level or lowest molecular orbital should be alpha plus 2 beta. Okay, and in this case, the energy of these two which are degenerate, the energy of these two level is alpha minus beta. Okay, so let me draw in this manner. So for cyclopropenyl cation, we have a molecular orbital having lower energy, whose energy is alpha plus 2 beta, and we have two degenerate orbitals having higher energy, whose energy is alpha minus beta. Okay, and you know very well in cyclopropenyl cation, only these two pi electrons are involving in the delocalization, right? Therefore, in each molecular orbital we can place 2 electrons, right? So I'll place 2 electrons here. We have only 2 electrons now. I'll place the 2 electrons here, and you know very well the Huckel approximation or Huckel method is applicable only for pi electronic systems. Okay, pi electrons, it is not applicable for sigma electrons, you know very well. So I place the 2 electrons here. Now what is the pi electronic energy? Pi electronic energy is, see, in the lowest energy molecular orbital we have 2 electrons. For each electron the energy is alpha plus 2 beta. So I have 2 electrons now, so 2 into alpha plus 2 beta, right? Plus, is there any electron here? No. So there are 0 electrons in the degenerate level, and the energy of that level is alpha minus beta. Since it is 0, you need not consider. So multiply this by 2, so we'll get 2 alpha plus 4 times beta. This is the pi electronic energy of cyclopropenyl cation. Okay, so the correct answer for this question is option A. Option A, right? Take down. Yes, what's the question given? The unperturbed energies in electron volt of a 3-level system are: energy of the ground state is 2, energy of the first excited level is 4 electron volt, energy of the second is 6 electron volt. The matrix elements of a perturbation V, the symbol V indicate perturbation between the levels are the interaction between 1 and 0, that is ground state, and the first excited state. That perturbation is 4, perturbation energy, and 2, 0 is 6, 1, 2 is 10. Okay, the question asked here is the second order correction to the ground state energy in the presence of perturbation V is. So V is the perturbation. Because of that perturbation, okay, we get say interaction between ground state and first excited state, ground state and second excited state, and interaction between second and the first excited state. These interaction energies are given. what we have to do, we need to calculate second order correction to the ground state. Observe the questions carefully. They are asking second order correction to the ground state. So how to answer it? Okay. And second order correction, listen, this is how we write second order correction to any nth state. This is a general formula. Second order correction to any nth state is equal to summation. I have given this formula already. M not equal to n. N represents states. So mth state and nth state should not be equal. Okay, is equal to modulus of psi m naught h operator prime. It is the perturbation operator. In this case, it is v. Then psi n naught and square modulus of this integral divided by energy of the nth state minus energy of the mth state. Okay, this is the formula, right? But in our case, the system is a 3-level system. It's given clearly 3 levels. There are 3 levels. So this is the ground level whose energy is E naught. The next level whose energy is E1 and the higher level is E2. Okay, and energies of E0, E1, E2 are given here, right? And the question asked here is the second order correction to the ground state. So let me write that here. Second order correction to the ground state. So second order, that in the place of n I'll put ground state. So what is the second order correction to the ground state? Okay, and here we have only 3-level system. So this is the ground state and these two are excited states. Okay, how to calculate the second order correction to the ground state? Yes, now listen. So this is actually a matrix element, right? First, we'll do this for how the ground state interact with the E1. So in the place of m, we should put 1. In the place of n, we should put 0 because n is ground state now. So in the place of n, you put 0. In the place of m, you put 1. So you'll get psi 1 naught h operator prime and psi 0. That is nothing but v. This is a short way of writing. V 1 corresponds to m value and 0 corresponds to the ground state. Okay, so the value of this integral is also called matrix element. The value of this matrix element is V10. Take the square of it divided by energy of the n is nothing but ground state now. So energy of the ground state is 2. E0 is given, energy of the ground state is 2 minus energy of the first excited state. So we have taken 1 here. So first excited state energy is 4. Okay, we have summation, so plus. Now how the ground state interact with the second excited state? Interaction between these two. So in the place of m you put 2 and in the place of n you put 0. So we get as another matrix element which is V20. Take the square of it divided by energy of the nth state is 2, ground state. Okay, n is nothing but ground state. Ground state energy is 2 is given here minus energy of the excited state is 6. I'll put 6 here. Okay, then summation is there, so we should put plus, but beyond these two I don't have any other states to interact. Okay, so that's all, because they are asking the interaction, second order correction to the ground state. So how ground state interact with the other state we should see. You are not supposed to take interaction between these two. Okay, our focus is only on ground state. So how ground state interact with this, how ground state interact with this, only these two we have to consider for this system. Okay, so that's all. Now what's the value of V10? V10 matrix element value is given already. So 4 square, let me write once, 4 square by 2 minus 4 is minus 2 plus V20 is 6. So 6 square by 2 minus 6 is minus 4. So what we get is 4 square is 16 by minus 2 plus 6 square is 36 by minus 4. So we get, if I cancel this, I'll get minus 8 here and here I'll get minus 9, right? So minus 8 minus 9, it gives me minus 17. Minus 17 electron volt. Yes, the correct option for this question is option C. Okay, take down. So for this question, the correct option is C, minus 17 electron volt. Right. So we'll move on to the next question. Question number 5. Yes, students. Just go through this question. In a three-dimensional isotropic harmonic oscillator, the degeneracy of the state with the energy equal to 9 by 2 h cross omega is, where omega is the angular frequency. 4 options are given. Yes, how to solve this? And this question appeared in 2024 December. Yes, how to answer it? Okay. See, I have discussed about isotropic oscillator. Listen, what's the energy formula for isotropic oscillator? Do you remember the formula? Energy of the isotropic oscillator? Nx plus Ny plus Nz plus 3 by 2. Do you remember this? Into h nu, correct? See,
Yes, sir.
yeah, in the first class or okay, where Nx, Ny, Nz, they are all quantum numbers. They can take value. Nx can take value 0, 1, 2, 3, etc. Ny can take value 0, 1, 2, 3, etc. And Nz can take value 0, 1, 2, 3, etc. 0, 1, 2, 3, etc. Okay. Now, in our case, the three-dimensional isotropic oscillator having energy n by 2 h cross omega. Listen carefully. What is h cross omega? H cross is nothing but h by 2 pi, and omega angular frequency is nothing but 2 pi nu. So you can cancel this 2 pi. This is nothing but h nu. Okay. So in the place of h nu, you can also put h cross omega. Nothing wrong in it. Right. So the energy is given now. So let me write like this: Nx, energy formula is Nx plus Ny plus Nz, okay, plus 3 by 2 into h nu. H nu, or I can also put h cross omega. I have told you both are one and the same. Is equal to the energy given is 9 by 2 h cross omega. Okay, so h cross omega we can cancel. Therefore, Nx plus Ny plus Nz, bring this plus 3 by 2 this side. So 9 by 2 minus 3 by 2. 9 minus 3 is 6. 6 by 2 is 3. So this is equal to 3. Okay. So Nx, Ny, Nz value sum should be equal to 3. So what are the possible combinations? We should check. We should find it out. Or, yes, or otherwise you can use this formula also. This is formula. This formula is applicable for third-dimensional oscillator, isotropic oscillator. G is equal to n plus 1 times n plus 2 by 2. Use this formula also. Okay, to get the value of degeneracy. What is n? Nx plus Ny plus Nz. This is nothing but n. So n value is 3 now. If n is 3, what's the value of G? Tell me. If n is 3, 3 plus 1, 4. 3 plus 2, 5. 5 by 2. So what's the answer?
10.
10. Yes, that is the degeneracy of this level. So correct option is D. Okay, take number. The lowest energy pi molecular orbital of butadiene has an energy of, beta is resonance energy, lowest energy of pi molecular orbital of butadiene. For linear conjugated systems, we can write energy of the kth pi molecular orbital, right, can be written as alpha plus we have direct formula, so you can use this. Alpha plus 2 beta into cos k into pi by number of carbon atom plus 1. Number of carbon atom involving in conjugation plus 1. Use this formula to find the pi electronic energy of any kth molecular orbital. Okay. Right. And what are the allowed values of k here? K can take value 1, 2, 3, 4, etc. Very simple. Now, in the question, they are asking the lowest energy pi molecular orbital. Lowest energy means k should be equal to 1. So if k equal to 1, what's the energy? A1 equal to, as the lowest energy pi molecular orbital, alpha plus 2 times beta into cos. So in the place of k you put 1. 1 into pi is pi by, and it is given butadiene. So number of carbon atom is 4. So 4 plus 1, it is 5. Okay, we need to find the cos pi by 5, right? So this is alpha plus 2 beta and cos 36 degree. We need to find out this. See, we are all familiar with the cos 30 and cos 45. Anyone tell me what's the value of cos 30 degree? Cos 30 is root 3 by 2, correct? Root 3 by 2. Root 3 is 1.73. So 1 by 2 is roughly 0.8. Right? Cos 45 is 1 by root 2. Right? It is roughly 0.7. So the value should be in between 0.8 and 0.7. So it should be, I'm sorry, I made a mistake. So correct, the value should be in between this, so it is roughly 0.85. I'm sorry, 0.75, like that, 0.75, because cos 36 degree is in between this, correct? So it should be between 0.8 and 0.7, so it's roughly 0.75. So if you take 0.75 here, and if you multiply by 2, I'll get roughly 0.8 something. I'm sorry, 1.6 something, correct? This value is 0.75. If I multiply this by 2 here, 0.75 into 2, you'll get roughly 1.5 or 1.6, like that. Okay. So this value cos 36 degree alpha plus 2 beta, this is roughly, I don't know what's the exact value. I'll just use rough value. So it is roughly 0.76 or 79, like that. Roughly 0.75. If you multiply this by 2, I'll get 1.5 or close to 1.6, right? So the energy of this orbital is alpha plus 1.6, because 1.6 is available. 1.618 beta. This is the energy of the orbital. Okay, this is the energy of the lowest pi molecular orbital of butadiene. But in all these options, alpha is omitted, right? Therefore, without alpha, the value is 1.618 beta. So the correct option for this question is option D. Option D. Right?
Sir, why alpha is
The question asked here is the expression for d orbital with n equal to 3, L equal to 2, m plus or minus 2 is the orbital wave function is given. It has normalization constant, and we have a radial part, we have angular part. The orbital generated from a linear combination of psi 2, 3, 2, 2 and 3, 2, minus 2. See, n, L values are same, m values are different. So now we should take the linear combination of these two. What linear combination? They have given a specific linear combination, 1 by I psi 3, 2, 2 minus 3, 2, minus 2. This linear combination we should take. That linear combination corresponds to which d orbital? That we need to find out. This question appeared in 2024 December. Yes, how to do this? A very simple one. See. So what we should do? We should take this linear combination, 1 by I times psi 3, 2, 2 minus psi 3, 2, minus 2. This linear combination we should take. Okay. So which is nothing but 1 by I. I'll take 1 by I as such. What is psi 3, 2, 2? Psi 3, 2, 2, n r prime r square sine square theta e power for 3 to listen, last m value is plus 2. So if we put plus 2 here, I'll get plus 2i phi minus remaining parts are same. Okay, remaining parts are same because only the plus 2 m values are different. M plus 2 for one wave function and m minus 2 for other wave function. Okay, and we should subtract and psi 3 to minus 2. How it looks like? Normalization constant n r prime r square sine square theta into e power minus 2i phi. This linear combination we should take. So here n r prime r square, these are all constant terms, you can take it out. So 1 by I. To find the orbital, we should keep the angular part. You should analyze the angular part. So I'll remove the radial part from here. So n r prime r and r square, I'll remove it. Okay, for time being, I'll remove the sine square theta also, sine square theta. Okay, and what we left with inside the bracket is e power plus 2i phi minus e power minus 2i phi. Okay, it's a very simple one. Now listen, 1 by I, normalization constant, radial function, r square, sine square theta. Okay, and here you apply Euler's theorem. E power 2i phi can be written as, according to Euler's theorem, what is e power I theta? Okay.
Yes, sir.
So what I did here, I used the wave function for psi 3 to 2 using the given information, and I used the wave function for psi 3 to minus 2. Then I removed the common terms out, and we left with e power plus 2i phi here and minus e power minus 2i phi here. Okay, apply Euler's theorem. So e power plus 2i phi is cos 2 pi 2 phi plus I sin 2 phi. E power minus 2i phi is cos 2 phi minus I sin 2 phi. We have minus in front, therefore this become minus and this become plus. So these two cancel, plus cos 2 phi minus cos phi cancel, and if I add these two, I'll get 2i sin 2 phi. Okay, let me write in the next page. Just copy down after this. Yeah, listen. So we'll continue this here. We'll continue here. So what's the value? 1 by I, normalization constant, radial function, r square, sine square theta into, if I add these two, I'll get 2i sine 2 phi. This I and this I cancel. These are all constants, so you can take it out. Okay, these are all constants, right? That doesn't going to determine your orbital, so you need not worry about that. So you can keep it in front. So 2n r prime r square. You keep these terms out. Now what we left with here is sine square theta and sine 2 phi. See, sine square theta and sine 2 phi. I am going to focus on this. Okay, we have already discussed it, but anyway, to find the orbital, what to do? See, you can write sine square theta as sine theta into sine theta. Correct? Sine theta into sine theta is sine square theta. Sine 2 phi can be written as 2 sine phi cos phi. Trigonometric formulas. Okay, you know very well. Anyway, 2 is a constant, you can keep it out. So 4n r prime r square. And now listen, I have sine theta, sine phi cos phi. Remember, sine theta cos phi, right? What is x, y, z in terms of spherical polar coordinate? X is equal to r sine theta cos phi. Am I right? So the sine theta cos phi combines to give x. And what is y? R sine theta sine phi. So sine theta sine phi combined to give y. So this orbital corresponds to d orbital with the xy coordinates. So it is dxy. Right? So this orbital is a d orbital, right? Very specifically dxy orbital. So the correct option for this question is option B. The orbital is dxy orbital. Okay. I stop here. We'll continue the remaining questions in the next class. Okay.